Hello, Chem 213 students, and welcome back for our second lecture video this week, which is part 4 of Chem 212 review. When we left off last time, we were ending at the end of chapter 8. It was alkene reaction review, and so we covered each of these reactions and also mentioned which ones it's important to know the mechanisms for, and it really helps you understand why reactions occur the way they do. For example, these three, the hydroboration oxidation, this one, or sorry, the oxymercuration demercuration, the halogenation here, the bromination, and the anti-dihydroxylation all occur in an anti-fashion because they proceed through a triangular type intermediate where nucleophilic attack can only happen from the bottom. Using that strategy helps you to not only memorize these reactions results without context, but to understand the way that they happen so that they stick in your memory better. And we're going to continue that strategy as we learn more reactions and we move on into alkyne reactions today, chapter 9. We're going to move into radical reactions, chapter 10, and we'll finish with chapter 11 that has to do with synthesis and provide a few tips on how to approach synthesis problems. So for alkynes, alkynes are those molecules that have a carbon-carbon triple bond, and a key feature of alkynes is that they are more acidic than alkenes and alkanes. Here, if we consider acidity in terms of REO, when we think of REO, again, we evaluate the stability of the negative charge after a potential acid has been deprotonated. And we look at this carbon. This carbon here is an sp2 hybridized carbon atom, or sorry, sp hybridized carbon atom, where it has, in one of its hybridized orbitals, it has this lone pair, and in the other, that is involved in the sigma bond that is in this triple bond with two other pi bonds also existing due to the unhybridized p orbitals. Remember that according to REO in the orbital, in the smaller orbitals like sp hybridized orbitals, these lone pair electrons are closer to the carbon nucleus, which allows them to hold on to that negative charge a little better, or actually significantly better, stabilizing this resulting anion when the alkyne is deprotonated. This is not the case when you have an alkene, such as this one, when you have the sp, so this is a carbon. Here you would have the, and I should have used red for that, but here this carbon would be sp2 hybridized, this one is sp2 hybridized. Likewise, this was here. And so there, this lone pair of electrons resides in a larger sp2 orbital. That means that it is not as close to the nucleus and not as tightly held, and thus much more reactive in terms of grabbing back a potential proton. We have a proton here that can go and grab it back. So that's one key feature of alkynes, is that terminal alkynes that have a hydrogen atom attached to the sp hybridized carbon are significantly more acidic than those hydrogens on alkenes and alkanes. What this means is that they can be deprotonated. Now, let's look at the bottom example first. Hydroxide ion, although a quite strong base in aqueous solutions, the strongest you can have, it's not sufficiently basic to deprotonate an alkyne. So this bottom reaction, we can see it has a little arrow, the big arrow here pointing backwards, meaning that this reaction does not go forward as well as it stays back the other way. And we can see why this is if we do a proton transfer from the hydroxide, leaving these electrons on the carbon. We have now sodium ion, and we also have the anion being this so-called alkylnide ion. and then the hydroxide has been protonated to produce water. If we look at the pKa of water or any, any acid in which the negative charge would ultimately lie on the oxygen when it's deprotonated, these are going to be significantly more acidic than any of these alkynes, alkenes, or alkanes. The oxygen atom stabilizes negative charge much, much more due to its higher electronegativity. However, if we use even a stronger base than hydroxide, we can deprotonate the terminal alkyne. And so here we have an amide ion, and this one can go and grab a proton from the acid here, and then we get the protonated alkyl amide, which is ammonia, and we get the alkylnide ion again here. And there, ammonia, with ammonia, remember nitrogen, it's hard to use REO exactly the same as you do with the others. But if we look at the pKa's, we can see that the pKa of ammonia is significantly lower than that of the ethyne. And so this reaction will, as all acid-base reactions do, it proceeds from the stronger acid to produce a conjugate base here. And the conjugate base that reacts is then protonated to create this weaker acid, ammonia. So the reaction goes from the stronger acid to the weaker acid. Here, the stronger acid to the weaker acid, meaning that this deprotonation with amide will move forward, but with hydroxide it will not. Okay, and so in terms of strengths of bases, remember, the weaker the acid, the stronger the conjugate base. So a carbanion on an alkane here will be extremely basic because it is the weakest acid when it's protonated. So the conjugate acid here is the weakest acid, making the conjugate base here the strongest base out of these that are listed. In terms of pKa, ammonia is shortly behind at 38, and so the fact that this acid is so weak makes the base particularly strong. Hydrogen has a pKa of 35, so hydride ion, also very, very basic. Then we have the alkyne here with a pKa of 25, meaning that this base is not as strong as these, not as strong as these, yes, but it is a stronger base than the rest of these, all of these containing negative charges on the oxygen ion. That oxygen ion, according to ARIO, ARIO, here with atom, the atom oxygen eating the atom carbon here. So these bases will deprotonate a terminal alkyne, being stronger bases than the alkylnide ion. Now, in terms of the reactions of acids of alkynes, most of the mechanisms are not known. So we're going to cover a few of the known mechanisms, and then we'll discuss all of the reactions, including the ones for which the mechanisms are completely known, and you ought to know the mechanisms, and also the other reactions where the mechanisms are not completely known, or only partially known, or not known at all. And there you simply would, by the empirical evidence, decide what the product would be. So when it comes to reducing an alkyne or adding hydrogen atoms to it, this can be done in a syn fashion, and this can be done by a soft hydrogenation. H2 would actually completely hydrogenate it. But if we want to do an anti-addition, we would want to use the so-called dissolved metal reduction reaction. And this includes dissolved sodium metal, which has a single electron, and so that initiates a radical reaction. We're going to be discussing radical reactions in more detail when we discuss chapter 10, but when we talk about radical reactions, we use these fishhook arrows that have instead of a double-headed arrow at the end, they have a single-headed arrow representing the movement of one electron. And so the first step in this mechanism is that the sodium atom provides one electron to a carbon, and then one electron comes from one of the pi bonds in the triple bond. The other electron goes on the neighboring carbon, and then we have 2 electrons in one unhybridized, or in one hybridized, one unhybridized orbital here, and we have 1 electron here. In fact, sorry, this is now a hybridized orbital, this carbon being like an sp2 carbon with only one unhybridized orbital remaining. At that point, we initiate an ionic reaction where this lone pair here is a member of a carbanion. This is done in ammonia so that the ammonia may be deprotonated. And remember why we use ammonia. We want to avoid having the deprotonation go in the opposite direction. So there's a proton transfer here. We use a double-headed arrow. These 2 electrons create a bond with this hydrogen, and it leaves as a proton, leaving these 2 electrons on the nitrogen, making an amide ion, which is not acidic at all. And so we don't have to worry about those kinds of reactions. Finally, another atom of sodium provides its second electron, and this creates another carbanion, which can then do a proton transfer with another molecule of ammonia. And now you have hydrogen added to each side of the double bond, or each side of the triple bond here, in an anti-fashion. So one is on either side of the double bond. And we ultimately get a double bond here. If you do a rough hydrogenation with hydrogen and platinum, like we talked about in the alkene chapter, this is going to hydrogenate all the way back down to an alkane. So if we want a syn addition of hydrogen, or sorry, anti-addition of hydrogen on an alkyne, produce an alkene, we would use the dissolved sodium reduction. So here are the steps, one of the steps in detail here. This first step is really key. We get this note here in this first step that we have electrons in this orbital here and we have an electron here. These position on opposite sides to one another to avoid a kind of interaction here, repulsion between the electrons in each of these orbitals. And it's important to remember that first step because that's what results in the formation of the transalkene. That repulsion of these 2 orbitals here, which would be higher in energy. So this formation occurs instead in the way in which these electrons in these orbitals would be positioned on opposite sides. This is a great way to remember why the sodium dissolved sodium reduction results in the trans addition of hydrogen. And then ultimately we have the protonation, the movement of the electron here from the sodium, single fishhook arrow, note that. Finally we get the protonation to produce the transalkene. And so that is an important thing to remember to help you understand why, important mechanism to help you to understand why the dissolved sodium reduction results in the trans addition of hydrogen. For all of the possible reductions, remember my use of the word reduction. Reduction can mean, if we're doing things very simply, a couple of things. Reduction would be the loss of oxygen from a molecule, or a gain in hydrogen, or a gain in bonds to each of these atoms. And an oxidation, as it sounds like, would in an organic reaction usually involves a gain of oxygen atoms or a loss of hydrogen atoms or bonds to those atoms. And so these are all involve various reductions. As I mentioned, if we use hydrogen and platinum like we would on an alkene here, this is going to reduce the alkyne completely until it gets reduced. It gets 4 hydrogen atoms added and produces the alkene. So if we want to only partially reduce the alkyne and produce an alkene, we have 2 options. We can use a poison catalyst such as Lindlar here, and so H2 Lindlar here will add hydrogens in a syn fashion so that they're both on the same side of the double bond, whereas the dissolved sodium reduction will add a hydrogen on either side. And remember that understanding the mechanism really makes this so you don't have to do straight up memorization. Plus, you are asked about mechanisms on the final exams, on midterms of final exams, and also on the ACS exam, specifically and directly. So another type of addition we can do is hydrohalogenation. And so this has a direct parallel to the hydrohalogenation in an alkene. Remember that the halogen atom would go in the more substituted position, and the reason being is when you first had the initial protonation of the alkene, like this would produce a carbocation intermediate, and that carbocation intermediate would be best positioned for greatest stability at the secondary carbon, which it would make a much more stable carbocation intermediate than at the primary position. And then that could be followed up by a nucleophilic attack by bromine. We can do an addition to an alkyne. If we do a single addition, again, the X here, the halide, will be in the more substituted position, and we could get a double bond. We'd get about 60 to 80% of this product. However, if we use a excess of the HX, we will add twice. We'll do this addition, and then we'll do another addition. In the second addition, we'll add a second halogen atom on the same carbon to produce a so-called geminal dihalide. The word geminal means on the same carbon, attached to the same carbon. So now regarding the mechanism is not completely well known. If this mechanism was analogous to the addition of HX in the addition, the hydrohalogenation of an alkene, then it would look something like this. It's important to note that this is not the mechanism, because we can tell it's not because it would produce a vinyl carbocation, and these are extremely unstable. And so this would be an extremely slow reaction if it were to occur this way. Kinetic data suggests that there must be a different mechanism. And the book does suggest an alternative mechanism where it's a trimolecular mechanism with two molecules of HX reacting with the alkyne at the same time. But trimolecular mechanisms, they require the simultaneous collision of three separate molecules, which by their nature makes for slow reactions. So in the end, we don't really understand the mechanism. But whatever it is, it's definitely not this. Otherwise, the reaction would not proceed as readily as it actually does. And so the kinetic studies, as I said, they indicate a tertiary mechanism, second order with respect to HX, first order with respect to the alkyne. This termolecular mechanism could look something like this, but it's possible that there are several competing mechanisms as well, because this termolecular mechanism requiring the collision of three molecules simultaneously in the right orientation would also lead likely to a very slow reaction, which is not what we observe. For the hydrohalogenation of alkynes, if we want to ultimately produce, so notice that the result here, when we looked, the result here was we had the halogen here adding in this secondary position. What if we want the halogen, we want to make sure that the halogen here gets added in the anti-Markovnikov position at the end instead of in the middle. And like with the alkenes, we would use a peroxide along with the hydrohalide to create this this situation where we have the halogen atom adding to the carbon at the end rather than the carbon right here. So it's not adding on the second carbon, the more substituted carbon. Instead, it's adding on the end, and we would get both potential isomers where the bromine is positioned on the opposite side here on the double bond, the so-called E and the so-called Z. So this would be Z, or on the same side, like we talked about last week, or E, meaning on the opposite side here. This will only work with HBr, and the mechanism here we'll talk about in just a moment. And the mechanism will help a little bit with understanding the way this works. We'll talk about the mechanism with respect to alkenes. Now, if we have a dihalide, and so if we add excess HX, we can turn the alkyne into a dihalide. And if we have a dihalide, we can get an alkyne. And so having a dihalide is quite useful for creating the alkyne. What we will do is we would have excess of the amide ion and water to finally protonate. And so we would do that. This would be a very, very strong base, which would allow us to do an elimination twice. And then ultimately we would use water to finally protonate the alkylnide ion. We can also do a oxymercuration, or sorry, acid catalyzed hydration here with mercuric sulfate as here also in a reagent here. And so the alkynes can undergo acid catalyzed Markovnikov hydration or addition of water. The process is catalyzed by mercuric sulfate because otherwise the reaction rate would be slow due to the formation of the vinylic carbocation. Remember, vinylic being at the position right on the double bond. And when this happens here, we have a hydration, meaning we're adding water, and the OH would be added to the more substituted position and the H to the less substituted position. And this would give us an enol, meaning a alkene with an alcohol attached in this vinylic position. However, this is going to undergo a so-called keto-enol tautomerism. And ultimately, instead of getting the alcohol, the enol, you're going to get a carbonyl instead. So the way this works is first the mercury 2 ion gets involved to catalyze this reaction, and this helps to stabilize the carbocation intermediate by having some of the positive charge here reside on the mercury. And so we have first a nucleophilic attack from the pi electrons in the alkyne, these attached to the mercury, and then we have a positive formal charge on this carbon, which is now involved in 3 bonds with no lone pairs, and the mercury now has given up one of its electrons in a sense by sharing them, and now is now a positive 1 formal charge instead of positive 2. It is in fact actually got one of the electrons rather from this pi bond. At that point, the vinylic carbocation here can undergo a nucleophilic attack by the water, and the water there would now, when these 2 electrons here create a bond with this carbon, that's going to make an oxygen that has 3 bonds and 1 lone pair. So that has a positive formal charge. Remember, whenever you have a neutral nucleophile attack, you're going to end up with a positive result, positive formal charge result. And so in the case of water here, this is going to require a subsequent deprotonation. So here, this water here grabs this proton. These 2 electrons are left behind the oxygen. And now the oxygen has 2 bonds and 2 lone pairs, and so it is neutral. And at that point, the hydration can continue. So we've gotten all the way up to this step now. Now the final steps are going to involve a protonation to complete the addition of water. So we've added the OH, and now it's time to add the H. And remember, in that last step here, when well, this is all acid catalyzed anyway. There's plenty of acid around, but we say it's catalyzed because that acid is recovered in this reaction up here. But then we can have this protonated here by grabbing a proton from remaining acid, of which there's plenty because this is happening in an acidic environment. And that proton ends up being attached right here. And so now this carbon here, which had no hydrogens attached, it now has 3 bonds and no lone pairs, so it is positive in formal charge. So it is appropriate here to take these electrons. This is an electron that is adjacent to a carbocation, electron pair adjacent to a carbocation pair. So we can do a resonance arrow here, which shows the electrons here in pi bond, but that leaves this oxygen with 3 bonds and 1 lone pair, meaning a positive formal charge. At that point, the mercury can leave as a positive leaving group here, and we say that it's catalyzed by the mercury because now the mercury is recovered at the last step and can be used again and again in the reaction. So it leaves, and it leaves a pi bond here, and then these electrons here now are pi electrons between 2 atoms of differing electronegativity. So those can be, again, repositioned there. And now we have the enol here. And now we have some potential, an additional potential reaction, because these enols are actually not particularly stable. So whether they're in an acidic or a basic environment, they're going to undergo a kind of conversion called a keto-enol tautomerism. And in that conversion, this hydrogen atom is going to jump over, and we're going to end up with a double bond here to produce a carbonyl. So this can happen in two ways. If this is occurring in an acidic environment, we'll start by a nucleophilic attack, or rather a proton transfer, from the pi bond here to grab a proton, and then these electrons will be left behind here, creating water. At that point, we will have the hydrogen attached right here. The hydrogen is now right here. And so this carbon, which had 4 bonds here, a double bond and one more and one here, the 4 together, and no bonds to hydrogen, now has 3 bonds and no lone pairs. So it has a positive formal charge, and we have a positive formal charge adjacent to a lone pair, so we can initiate a resonance arrow here. This is one of our 5 resonance patterns. But at that point, the way we've drawn it, we have a double bond here to oxygen, so that's 2 bonds and one more, 3 bonds to oxygen and 1 lone pair. So this oxygen has a positive formal charge, and thus it would be more stable if it were deprotonated. And so this is acid catalyzed, because the acid will now be recovered when the water in this aqueous environment removes a proton. So there's a proton transfer, it grabs a proton, two electrons are left behind as a lone pair on the oxygen, and now we get the carbonyl. And this carbonyl happens to be significantly more thermodynamically stable than the enol. So you're going to have really a lot more of this once equilibrium is established. This can also be catalyzed by a base. The way it is catalyzed by a base is that if you look at an alcohol and a hydroxide, these are very, very similar in terms of pKa. So you can see there's going to be a double-headed arrow here, meaning there's a very equivalent equilibrium where you're going to have about half of these hydroxides go and deprotonate this alcohol. So you will get a significant concentration of this. And then this equilibrium will be driven forward by a second step. In that second step here, we have a kind of resonance here. In this resonance step, we're actually showing 2 resonance steps at once here. One here is a lone pair here, and it is between electrons or atoms of significantly differing electronegativity. These electrons here are delocalized, can go to represent a pi bond here, and then these electrons are behind here. In reality, we've got delocalized electrons across all these sp2 hybridized atoms. There is sp2 hybridized carbon here, sp2 hybridized carbon here, and this oxygen is sp2 hybridized. This electron is residing in a unhybridized orbital, and so it can also be drawn as having a double bond here. We have now a carbanion, extremely basic, so that will go and deprotonate water and then leave hydroxyl. This really drives a lot more forward than it does backwards, even though we can write a double-headed arrow here. And ultimately, we get the carbonyl. So this keto-enol tautomerism can be both acid and both base catalyzed here, and you'll get either way a carbonyl product. So one thing to remember is that when you're hydrating an alkyne, you're going to produce an enol, which will then undergo a tautomerism to produce a carbonyl. You have to keep that in mind. The product of these hydrations of an alkynes are in fact carbonyls, aldehydes, or ketones, and not alcohols. Finally, there's a very synthetically useful reaction that can occur because the alkynes can be deprotonated quite readily by a very strong base. Specifically, amide is usually the base. Note this nitrogen has 2 bonds to hydrogen and 1 lone pair, leaving it this -1 formal charge. And this can deprotonate the here. In fact, actually, there's another. Not one lone pair, two lone pairs. That second lone pair is not drawn, but essentially you've got 6 atoms on a nitrogen, or 6 electrons on a nitrogen that should have only 4. So you got a negative, only 5 rather. You have a -1 formal charge. So you can have a proton transfer here. This is a much stronger base than this alkyl ion, so the proton's removed, and we leave these 2 electrons behind, leaving a carbanion here. And then that carbanion can behave as a nucleophile. It's a great nucleophile. So if you have a polar bond here, where we have, in this case, an alkyl halide, the halogen atom is pulling electrons this way, making this side partially negative, where the halogen atom, and this side partially positive. So this negative formal charge wants to go and attack the alkyl group, the carbon attached to the halogen atom, and we get a nucleophilic attack here in an SN2 style. It's basically just an SN2. And now we add this whole alkyl group. All of these carbon atoms are now added as a chain on the end of our alkyne. And that is our first way that we have of producing a longer carbon chain with more carbon atoms. We react an alkyl ion with an alkyl halide. So now we have a summary of all of the alkyne reactions, and let's just kind of go through and talk about which ones we spoke specifically about their mechanisms. You'll note that the mechanisms for alkyne reactions are a lot less known than those for alkenes. We had a kind of wishy-washy types of semi-descriptions of their mechanisms, but the only mechanisms that we saw in detail were those that involved the mercury, the mercury and acid catalyzed hydration here, which ultimately produced, remember, not an alcohol, but instead a carbonyl because of the keto-enol tautomerism. And we also discussed in some detail this sodium reactions right here, the dissolved sodium reduction, right? And ultimately, we also discussed how we could deprotonate. It's not written here specifically on the summary. Oh yeah, here it is right here. We discussed this mechanism where we could deprotonate the alkyne and then have it react with an alkyl halide and produce a alkyne with more carbon atoms attached on one side. And those were the only ones we knew the mechanisms for completely. For the rest of them, we have to just basically do comparisons to other to alkene reactions. So if we had an alkene and we were hydrohalogenating it, we'd produce a alkyl halide in which the halogen atom was attached to the more substituted carbon. This we would say it's a Markovnikov addition. And in fact, we do get Markovnikov addition of hydrohalides too. The halogen atoms goes on the more substituted carbon and we're left with an alkene. In the case of the acid catalyzed hydration, we end up with a carbonyl for the reasons that we discussed instead of an alcohol here, and it is at the more substituted position. If we want a carbonyl at the less substituted position, this has a direct analogy to what we did in the alkene chapter, where when we wanted to hydrate and have the OH group at the less substituted position, we would use hydroboration oxidation. And in this case, if we want the carbonyl here to go at the less substituted position rather than the more substituted position, we would also use the hydroboration oxidation. Notice that instead of BH3 here, followed by hydrogen peroxide and sodium hydroxide, a alkylated borane is used. Instead of 2 hydrogens here, we have 2 R groups. And this is the big difference here between the reagents that we're using for the hydroboration oxidation of alkenes versus alkynes. And this allows for it to only add water once and subsequently produce the carbonyl. We can do a halogenation. If we do a halogenation here, it's simply the same as an alkene. We add 1 halogen atom on each carbon, and like it would be on an alkene, they add in the anti-fashion. So you can make a direct analogy to the alkene there. The halogenation would happen in the anti-fashion, on the alkene. It will also happen on the alkyne to produce the E isomer on the alkene that's produced. The mechanism is not known, but the result is the same. So you can kind of think of the alkene mechanism and apply that here. If we use excess halogen, here carbon tetrachloride being the solvent, we'll get double halogenate. And we'll have 2 halogen atoms added to each carbon. Ozonolysis can also be done like it's done on an alkene. On the alkene, you get 2 carboxylic acids. However, in the terminal alkyne, you'll get a carboxylic acid here, and you'll get a carbon dioxide instead. And we discussed the dissolved sodium reduction here. Well, let's go to this one here. If we want to make a terminal alkyne longer and add more carbon atoms, we can deprotonate it and react with an alkyl halide like we saw before. If we want to do a anti-addition of 2 hydrogens, so instead of a syn addition, we put 1 hydrogen here, 1 hydrogen here on opposite sides of the double bond. We use the dissolved sodium reduction, and remember, you should remember that mechanism because that helps you to remember why we get the anti-result. If we try to hydrogenate straight with just in a rough way with hydrogen and platinum, this will double add the hydrogen and completely reduce the alkyne to a alkane. If we want to do a syn addition of hydrogen, we should use H2 with the poison catalyst. Again, this is one where the mechanism is not completely known, and so it's not worth really thinking about the mechanism. You can kind of think of this in the same way that you thought of the hydrogen adding on the platinum surface. Because it's adding on a surface, the hydrogen have to add to one side because the other side is stuck to, or because it's that's the side that's stuck to the surface. The hydrogens are stuck to the surface of the platinum, and in this case, stuck to the surface of this catalyst. If we want to create an alkyne, we can use any dihalide, so either geminal or vicinal dihalides, and we do a double elimination with a very strong base, excess sodium amide, very strong base. Ultimately, we get the alkyl night ion deprotonated, so we need to follow up with water, which will protonate that alkyl night ion. And finally, if we use excess HX instead of 1 equivalent, we double halogenate both at the more substitute geminal dihalide. And that's a summary of the alkyne reactions. Let's move on to radical reactions now. So free radicals, free radicals are atoms or molecules that have an unpaired number of electrons, an uneven number of electrons. It has unpaired electrons. And these are generally initially formed when a bond is struck by UV light, high energy light, and this will homolytically cleave the bond, meaning one electron will go to one atom and one to the other, instead of having both electrons go to one atom. And as we saw in the Chapter 9 review, when we have one electron moving somewhere, we use a fish hook arrow, as opposed to the double-headed arrows, which indicate the movement of 2 electrons. So these are fish hook arrows showing the movement of 1 electron, and this homolytic bond cleavage produces 2 radicals, 2 atoms here that have a single, an unpaired electron to them. Now, like carbocations and like carbanions, we can have resonance involved when we have radicals, and we're going to look at a few patterns of resonance in radicals, 6 patterns in fact, as opposed to the 5 that we saw for the ionic types of molecules rather than radicals. And we use fishhook arrows to represent the movement of the electrons between these unhybridized orbitals. So 1 electron here comes from the pi bond. 1 electron is this radical electron that is now drawn as a pi bond on the left. And then one of those electrons gets left on the other side. And so that's this one right here. So this is an allylic radical, meaning 1 position away from the double bond. And so we can have, like radicals like carbocations are stabilized by resonance. Now, when we talk about the radical mechanisms, as I mentioned, a little bit off. I talked about the resonance patterns. What I meant to say was unlike the 4 ionic reaction mechanism arrows, we're going to have 6 for radical reactions. The first of these is the homolytic cleavage that we saw before. So when we expose a molecule to a lot of heat, like in the engine of an automobile, this occurs a lot, or to high energy UV light, like in the sun, we can have the homolytic bond cleavage, in which one electron in the bond goes to each of the 2 atoms in the bond. Another type of reaction arrows for radical mechanisms is addition to a pi bond. So in the addition to a pi bond, we have a radical molecule reacting with a neutral molecule. And in the radical molecule, one of the electrons goes towards making a bond with one of the atoms in the neutral molecule that's involved in a pi bond. So this is an addition, which will get rid of the pi bond, and that will then create a single bond here. The remaining electron of the pi bond is now placed on the other carbon in the bond. And so we have a radical reacting with an alkene to produce a single radical molecule. The third type of pattern in radical mechanisms is the hydrogen abstraction, and this is where a halogen atom removes a hydrogen atom from an alkane or another organic molecule. So again, this is going to start with a radical and a neutral molecule like the last example. But unlike the last example, it's also going to produce a neutral molecule and a radical. And this will involve one electron from the radical going to create a bond to hydrogen, and one electron from the bond between hydrogen and the carbon atom go to creating a bond to the halogen atom. Then the one remaining electron in the bond is left on the carbon atom here in the organic molecule. Likewise, we can have a halogen abstraction. And so if we have a radical carbon atom here, this one electron can go and make a bond with a halogen atom, and then the bond between 2 halogen atoms in a halogen molecule here will then go and be used to create the bond with the carbon atom. The remaining electron in that bond between the 2 halogen atoms will then reside on the remaining halogen atom. And so in both of these two, number 3 and 4, we start with a radical and a neutral molecule. We end with a radical and a neutral. The fifth type of radical mechanism, part 2 radical mechanism, or pattern in radical mechanisms, is the reverse of the addition. So in the addition, we had a halogen atom, let's say, react with a carbon-carbon pi bond and produce a bond to the halogen atom. The elimination is the opposite of that. The halogen radical gets its electron back. Then the other electron in the bond to the halogen atom there goes into the pi bond, and the one remaining electron here goes into the pi bond. And we get the opposite of the addition. We get the elimination, where we get the halogen radical atom back, and we get the alkene back. Okay. Finally, coupling. Coupling is the opposite of homolytic cleavage. So whereas in a homolytic cleavage, the single bond would break here, and we'd get a single atom on each of these, we're actually doing the opposite here, and these 2 electrons are coupling here, and these 2 electrons are going to create a bond between the halogen atoms. And so in the opposite direction, it involves the breaking of that bond, exactly the opposite of what we observed. So those are the 6 patterns in reaction mechanisms, and we're going to see a lot of them here. The first example here, the first mechanism that we learn in the radical chapter, is the halogenation of alkanes. Now, this reaction is extremely important because alkanes do not have any polar bonds, which makes them spectacularly unreactive in ionic reactions, because ionic reactions depend on a negative area of the molecule attacking the positive area of the molecule. But if there's no negative or positive area in the molecule, you can't have a reaction. So whenever you're starting with an alkane, you're going to want to halogenate it if you want to initiate ionic style reactions with it. And that can be done by reacting the halogen molecule with the alkane in the presence of UV light. And the way this works, and this adds a halogen atom on to in replacing a hydrogen atom. So the way this works is it's started by an initiation. And for an initiation to occur in radical reactions, what you want is a relatively weak bond. And for halogen atoms, especially fluorine and chlorine, their bond is quite weak due to the high electronegativity of each atom pulling that bond apart. And so these atoms are both so electronegative, they each want to grab their own electron from the bond and break the bond. So if you give them a little bit more energy by shining them with UV light, you can initiate this cleavage, homolytic cleavage of the bond. This is followed by, and this is called an initiation step. So initiation will generally involve the creation of a radical. This will be followed by propagation steps. These steps are self-containing, which means they'll continue and continue and continue and continue. And so these make up the bulk of the reaction. You only need a few initiations to start the reaction. Then the reaction will actually proceed through propagation steps. And this is why if you want to find out what the overall reaction is, you add up the propagation steps, because those are the steps that are occurring again and again and again and again many times. And so here, this is going to involve a hydrogen abstraction by the chlorine radical that was produced. And so one electron here goes into creating the bond with the hydrogen, one electron from this bond, and you get a bond between the hydrogen and chlorine. And then one electron is left behind on the carbon, leaving a methyl radical here and hydrogen chloride. This can be followed up by a halogen abstraction because we still have chlorine as a reagent. And so if the chlorine encounters a highly reactive methyl radical, this will initiate a halogen abstraction where now the carbon will create a bond with the chlorine by using its radical electron and one electron from the chlorine-chlorine bond to create a bond between carbon and chlorine. And now we have recovered our chlorine atom. So notice how we don't have to have a lot of initiation, because once we have a few chlorine atoms, these will be self-sustaining in their own reaction. They'll be used up in the hydrogen abstraction, but then they will be recovered in the halogen abstraction, and they can be used again and again and again. Finally, the reaction will occur when the radicals are quenched or when they couple and they are no longer present. So there are several radicals that were produced. There were two radicals that were produced in this reaction: chlorine atom radicals and methyl radicals. So any of those could couple. If the two chlorine atoms encounter each other, they can couple to recover the chlorine molecule. If the methyl radical and the chlorine radical encounter each other, each of these two radical electrons can now go into creating a bond between carbon and chlorine. And if two methyl radicals encounter each other, these two electrons here, each of them can go into creating a bond here together between the two carbon atoms. Now, we're going to have a very small amount of methyl radicals at any one time, so we won't expect a lot of this produced, but there will be some. Our primary product will, in fact, be the methyl chloride, but not from this reaction, from this series of reactions here that produce chloride, the propagation reaction. So ultimately, if we want to know what the total reaction produced, we would add up the propagation reactions. Notice we have a chlorine atom on either side. The chlorine atom is used up, but it's reproduced. And so that is not involved in the reaction. Also, the methyl radical is produced in the first step, but it's used up in the second. So overall, our overall reaction is CH4 plus Cl2 right here produces CH3Cl and HCl, just like we had written previously. Oops, my head's in the way. That's CH3Cl, and I'll write it over on the left side, HCl. Okay. Now, notice that we used the chlorine here as a radical initiator last time, and the argument was that halogen-halogen bonds tend to be quite weak, either because they're particularly long in the case of iodine, or because even if they're very short, like fluorine-fluorine or chlorine-chlorine, they're a bond between two highly electronegative atoms. So they're quite weak bonds and can really easily be broken by some heat or some light. There are even weaker bonds that make for even better radical initiators. You may remember that when we wanted to do a anti-Markovnikov addition of a hydrohalide, or hydrohalogenation in the anti-Markovnikov fashion, with the halogen at the less substituted position, we would add a radical initiator like this, which would initiate a different mechanism, a radical mechanism, which will ultimately result in the less substituted product. And we're going to see that. And this can be done because peroxide bonds like this between two oxygen atoms are extremely weak, again due to the fact that both of these oxygens are extremely electronegative, and so they want to pull this bond apart by pulling on those electrons so hard. Likewise, we can get an even weaker bond here with an acyl peroxide because when it ultimately produces its radical, this radical is resonantly stabilized, and so it is an even more stabilized product. And so that makes it so that less energy has to go into creating this product, and thus we get more energy out, and the bond energy then is easier to break that bond. And it's most reactive, it's even effective at relatively low temperatures. One thing to note is that if we want to be selective with our halogenation, we should use Br2, and I'd say it's always probably a good idea to use Br2 because especially if we want to put the halogen in the more substituted position, we really have to use Br2. If we want a mixture of products where the halogen is in the more substituted position and the less substituted position, we would want to use chlorine. So the bromination here is going to be 100% adding bromine in the more substituted position, whereas the chlorination will produce a mixture of products. We don't do fluorination, so no F2, and that's because it will produce too violent of a reaction. And we don't use I2 because this is not going to be a spontaneous reaction. And so our options are chlorination and bromine. When it comes to the stereochemistry of this result, remember this is going to go through a radical intermediate, which is a flat trigonal planar situation. If we have a carbon radical with 3 bonds and one radical, one electron, and so we're going to get a racemic mixture of products because the chlorine can add equally from one side or the other, in this case, the case of a carbon atom. So make sure to indicate, if you only write one, for example, and you don't write the second on my exams, you'll want to at least write that the enantiomer is there to indicate that you're going to go both stereoisomer products. Of course, this last carbon here is not chiral because it has 2 hydrogens attached, so we don't have to worry about that on the terminal carbon there. In addition, if we have an alkene, the alkene will have a particularly stable radical situation. If we perform a hydrogen abstraction on the alkene, it will be the vinyl, or the allo rather, hydrogen that is removed, because this produces a resonantly stabilized radical here, where this radical is allylic to the pi bond, and therefore we can have one electron go into this pi bond here, the other electron showing this pi bond, and the remaining pi bond here. So these electrons are delocalized across this entire area here. And what that means is you can get more than one allylic bromination product. For allylic bromination, Br2 can be used, but Br2 is not ideal because it competes with the halogenation reaction, which adds 1 bromine to either side. And so instead, generally when we're trying to do allylic bromination, we use a reagent called NBS instead of Br2, because using NBS keeps the bromine concentration to relatively low. So we're not going to have Br2, we're just going to have bromine atoms, and this will add 1 bromine at the allylic position instead of adding 2 bromines across a double bond. So if we use NBS, we're going to get allylic bromination, but we do need to consider the resonance situation for the radical. So one note when that is particularly true is where we have the potential for a resonance situation that will result in a tertiary radical, because tertiary radicals are more stable than secondary, which are more stable than primary, much like the case for carbocations. And so here, in this case, instead of deprotonating or hydrogen abstracting rather at the vinyl positions, The most stable position is to deprotonate at the allyl position. And so if we have this bromide ion, we'll get a hydrogen abstraction, 1 electron. Whoops, I messed up that arrow. I was supposed to draw it from the bond. 1 electron coming from the hydrogen here, the bond with the hydrogen, and 1 electron coming from the bromide ion. Sorry, and this is supposed to be 1 electron here. It's a radical. And then we'll have 1 electron remaining, and that one will be in the allyl position. And now we have the potential for a resonance situation. Notice that this electron is allyl to the double bond here, and so we'll have 1 electron here, the radical, 1 electron from the pi bond, and then 1 electron is remaining, resulting with this electron here being in the primary position. So we can have halogenation not only at the tertiary position here with the bromine here coupling here with this radical right here, right in this situation. I should use blue here. But we can also have it coupling right here as well, producing this other product. Of course, the product with the tertiary position will be significantly greater, and this would be a major product here. This would be a relatively minor product, but you'll get a significant amount of both. And again, remember that you're going to get both isomers as well. So it would be suitable to say plus an enantiomer, or well, if it were chiral, which is not, because it has 2 of the same group, 2 methyl groups. So if this were a chiral carbon, you'd want to be sure to indicate that you also get the enantiomer. One other important radical reaction is that in which we have autooxidation. This is particularly occurs in ethers, and it results in explosive peroxides. The way the autooxidation mechanism works is that we have an alkyl molecule here, and we have some radical initiator like some of the 3. Halogen we saw, especially peroxides, and acyl peroxides. So we start with the initiator, which creates a radical, and then we get a hydrogen abstraction here. This leaves us with an alkyl radical. And then if this is occurring around oxygen, okay, so the oxygen itself can be the initiator too. And so if this bottle is just sitting open in the air, the oxygen will be involved. And here, instead of drawing the oxygen with a double bond, we've drawn it as a diradical, because remember, those oxygens really want to hog their electrons. And so they do sometimes behave like a diradical. And so this radical can couple with this other radical in a propagation step. The reason why this is a propagation step is because, and not a termination step, is because we still have a radical afterwards. And that radical can then go on to do a hydrogen abstraction from our substrate here, and leaving another radical. And finally, the radicals can terminate. And at that point, we've produced a peroxide here. And these peroxides are highly reactive. If we initiate, so in terms of the addition reactions here, another mechanism that we should be aware of. Again, if we're starting a reaction here with a peroxide, that peroxide can go and do a hydrogen abstraction from a hydrohalide, and that's what we see here. And ultimately, then we can add the bromine ion, and when we do, we add the bromine here, bromine radical, and this adds to a double bond here. It's going to add in the position that's anti-Markovnikov. It will add in the, and it's important to understand this mechanism, because this is going to help you remember here when you react one of these radical initiators here with HBr, you're going to get and you ultimately produce a bromine here. You're going to get a addition to a double bond here that's going to produce a radical that's in the more substituted position. And thus, ultimately, when the hydrogen abstraction finishes this off, the halogen is going to add in the anti-Markovnikov position. And this is why when you do the hydrohalogenation, so when we did HBr ROR, this explains why the addition occurred when we added the ROR in the anti-Markovnikov, or the less substituted position. It's because by adding the ROR, we add this radical initiator, which then produces the bromine atom here instead of adding the HBr. Now we have the bromine atom, which is a radical, and that does the addition instead of, remember, the alternative addition without the ROR. If we were adding with HBr, or HBr like this, we've drawn a line HBr. What at first occurs is that we have the addition of the bromine instead, and we have here the, or rather the, I wrote that wrong. We have the nucleophilic attack on the hydrogen. Sorry, I said that wrong there. But then that hydrogen is going to go in the place that produces the more stable carbocation, which is also at the tertiary position. And then subsequently, the bromide ion, rather than the bromide atom in this ionic mechanism, would attack at the more substituted position. But when we add the radical initiator, we instead end up with a situation where we've added the bromine and produced a radical. And that radical should go in the more substituted position. Bromine should go in the less substituted position to produce the more stable product. And that is why when you add the ROR radical initiator, you get the addition of the halogen at the less substituted position rather than the more. And that's what we learned in chapter 8, but this is the reason why. So noting this mechanism really helps to explain that. And so in terms of the propagation steps for this, you just saw that one. We get a bond between the bromine and the carbon, one of the carbons in the alkene. The radical is going to go on the more substituted carbon, and then we will end with the abstraction of the hydrogen to recover the bromine atom. And so overall, our reaction looks like this. Bromine is used up, bromine's produced here, and then this radical is used up, this radical is produced. So what we get overall in the presence of the ROR is this alkene plus the HBr produces this one here, the more substituted hydrohalide instead of the less substituted. Finally, this mechanism ends with termination by the coupling of the radicals. Lastly, radical polymerization is also initiated. So this is the way in which plastics are made. This is initiated by, again, the introduction of a radical initiator, and then there's, again, like we saw in the last example, an addition to the double bond, producing another radical here. That radical can go on to react with another alkene and do another addition, which produces another longer radical, which can add to another alkene here. And this goes on, producing long chains of atoms, long chains of carbon atoms. And this would produce, ultimately, what we see here would produce polyethylene, or this being ethene or ethylene, which is commonly called ethylene. And when we perform this radical reaction in sequence, we end up with polyethylene, very, very long hydrocarbon chains. Ultimately, the termination is either the coupling of a very long polyethylene radical with the radical initiator, or with itself producing a longer chain. It's important to note that often we can get a hydrogen abstraction by the radical, which will produce not a terminal radical, but a radical in the middle of the molecule, which can then go and react with ethylene and produce branches. And highly branched polyethylene makes for very tangled messes of molecules, which produces a more squishy squeeze bottle, whereas the unbranched polyethylene is much more stiff, like a bottle cap. So these are the reviews of the alkyl reactions. We covered the mechanisms for the hydrohalogenation in the less substituted position in the presence of a radical initiator. We also talked not about the mechanism in particular, but a little bit, and the allylic halogenation, and we talked about the halogenation simply by using the halogens and light, UV light, and that will produce the more substituted bromination here. The chlorination will give you a mixture of products. And remember there, you're going to get a racemic mixture. racemic of isomers if there is a chiral carbon. Finally, now that you have a lot of reactions, you'll begin to approach synthesis problems. And so when you're doing this, you're going to want to think about several things. First of all, do you have more or less carbon atoms? Because if you have more, there's only one reaction that we have so far that can make more carbon atoms, and that is the reaction of an alkyne with excess NaNH2 followed by water. So if we want to make a longer carbon chain, we're going to want to use that one. If we change the functional group, we're going to want to choose the kind of reaction that will give us the change we're looking for. Oftentimes, it's useful to look at the final product and work backwards. This is called retrosynthetic analysis. Instead of only moving forward, we also move backwards. And you still need to ask the same question. So, are we adding more carbons in this step, in the last step, let's say? Are we changing the functional groups? That's going to help us to decide which reaction is occurring and which intermediate this is going to come from. So for example, let's say we want to do a retrosynthetic analysis in which we start with this alcohol here and ultimately produce this alkyne. So let's ask the two questions. Number one, do we have more carbon atoms than we had before? Well, no. If we count the carbon atoms, we have 1, 2, 3, 4, 5, 6. 6 carbon atoms. And if we count them here, we have 1, 2, 3, 4, 5, 6. So we're not going to have to use that deprotonation of an alkyne in reaction with the alkyl halide that I had mentioned before. But is there a change in the identities of the functional groups? Well, absolutely, right? Basically, we're going to remove this OH here, and we're going to turn this area here into a triple bond, right? So we have to think, how is it that we're going to get? What are the steps we're going to have to take to get ultimately to the end here? And in this case, it's kind of hard to see from the beginning where we might go, but we do only know a few ways that we can create for ourselves an alkyne. And one of those, and in those, we're going to start with some type of dihalide, right? So maybe we start with 1, 2, 3, 4, 5, 6. We have 6 carbon atoms. And maybe we start with a dihalide here that has 2 bromine atoms. And this could come from the addition. And so if we had these, though, we could use XS NaNH2 here, and we could do a double elimination, and we can follow it up with H2O, and that would protonate it. So that would work here. So it's 1, 2, like that. And now see how it becomes a lot easier to work backwards. Well, how are we going to get a double dihalide like this? Well, we would want to probably react some kind of alkene with bromine, and we can use often we indicate the solvent here as CCl4. We don't have to, but often we do. And so the question now becomes, how do we perform here an elimination so that we can start with this alcohol here and we can get this alkene? And so remember, when we're thinking about this, we're going to have to do an elimination where the OH is the leaving group. And so we know that OH is a terrible leaving group, right? And so we're going to want to start with something that's a better leaving group. So what we can do is now we're kind of working forwards, because we can now replace here the OH with a tosylate group. And to do that, we would want to use tosyl chloride and pyridine. And then finally, we'll do an elimination here. So we'd use concentrated H2SO4. And we can do this. This will give us the more substitute product, because the OH is terminal. So H2SO4, or rather, we're doing an elimination. We could use any base here. So we could use sodium methoxide. We could use really any base, because this alcohol is terminal. And so I indicated tert butoxide here, which would be fine. We can use any other base too, or any other base. This will perform our elimination, but first we have to change the alcohol to a good leaving group. So tosyl chloride pyridine would work there, followed by Br2CCl4, and then finally the excess NaNH2 in water, and that completes our whole mechanism. So you can see here how working backwards sometimes really helps, but remember to ask yourself those fundamental questions. And also, when you're doing synthesis, you can keep my guide behind you, the guide I passed out recently, and that might really help. And so that's going to bring us to an end of our somewhat quick review. We spent over an hour here of chapters 8, 9, and 10. Finally, our last video will have a final review of chapters 12 and 13. I expect it will be somewhat shorter than this one, but I look forward to. I hope that this was useful to you, and I hope that you'll have a good use for this next video as well. I'll see you in the next one.